Nuclear power is the safest form of energy production, resulting in the fewest deaths per terawatt hour of electricity produced. Yet, according to a Pew Research Center poll, less than half of Americans view nuclear power favorably. Let's demystify this word nuclear and clear a few things up. An atom is composed of three smaller particles. The nucleus contains the positively charged proton and the neutron, which has no charge. Orbiting around the nucleus are the negatively charged electrons. A neutral atom will have an equal number of protons, neutrons, and electrons. Now we know that atoms can have different number of electrons than protons. If it has more electrons, it is negatively charged. If it has fewer electrons than protons, it is positively charged. Now here's where the nuclear stuff comes in. If an atom has a different number of neutrons than protons, it's an isotope. Many isotopes are stable. The strong nuclear force is what holds the nucleus of an atom together, and the strong nuclear force is the strongest of the fundamental forces. It's 6,000 trillion times stronger than gravity, so an additional neutron in some atoms won't cause it to break apart. But then there are the times when atoms have a radioisotope, meaning they are unstable and radioactive. In a radioisotope, the strong nuclear force is not strong enough to hold the nucleus together, and radioactivity is the result of an atom reaching a stable configuration by ejecting protons or neutrons or other particles or some other form of energy. There's a lot of ways to measure radioactivity, but the one you should be aware of is the half-life. The half-life is how long it will take for half of a radioactive material to decay into more stable atoms. When a radioactive isotope decays, it releases energy and matter from the nucleus, and it will transform to a different element if the nucleus splits. Some forms of decay are very dangerous as the energy emitted is very high and can damage the bonds in your DNA, which may lead to cancer. Isotopes with a short half-life decay faster, and therefore are more dangerous in the short term because they can emit more of this energy in a shorter time period. But the trade-off is that the entire substance decays to a stable, safe element faster. Elements with a long half-life will decay slower, thus releasing fewer harmful radioactive rays at any given time, but they will remain radioactive for a long time. And by long time, I mean like hundreds of millions of years. Just about every element above the atomic number 83 are naturally only found as isotopes and are radioactive. And those are the ones we use for nuclear energy, most specifically uranium. Now, uranium exists naturally as two different isotopes. About 99.3% of all uranium found on Earth is the uranium isotope 238, and 0.7% is uranium-235. Now, uranium-238 is radioactive, but barely. It has a very long half-life, and it's not particularly useful as a source of nuclear energy. Uranium-235, on the other hand, is a less stable isotope and has a shorter half-life, but more importantly, uranium-235 can be fissioned, meaning the nucleus can be split. When an additional neutron is forced into the nucleus of uranium-235, it will break apart into one atom of krypton, one atom of barium, and 3 neutrons. Now, those neutrons are important because as they hit other uranium atoms, it will cause them to break apart and release their neutrons, and so on and so forth. This is a nuclear chain reaction. This reaction also releases a lot of heat energy. Around 2.5 million times more energy than the burning of coal. Let's take a look at how this works when utilized for making electricity. In a nuclear reactor, there are 3 main components: the fuel rods, which contain the uranium, the control rods that contain materials that can absorb excess neutrons to slow down a nuclear chain reaction, and control the rate at which it occurs. and the containment building, which has multiple redundancies for safety in case a reaction does go out of control. The vessel itself is 9 inches of steel, then 3 to 7 feet of concrete, then another 2 inches of steel, followed by 3 to 4 feet of steel reinforced concrete. It is very difficult for anything to escape a nuclear reactor. The power generation itself is good old-fashioned steam power. The reaction provides the heat, water is converted to steam, the steam spins a turbine. Yep, even the most modern of nuclear power is just steam power. The amount of electricity produced by nuclear power plants has been steadily increasing until the 2000s, stagnated, and then has begun decreasing. The number of active nuclear power plants is projected to decrease by a lot by 2060, and much of this is due to public fear and uncertainty over nuclear power. Despite it still being the safest form of power generation, I can see where some of this public distrust comes from. Spent nuclear fuel rods are still radioactive and will remain so for millions of years, so the long-term disposal of them is difficult. And I think here is the thing that really concerns people. We know that nuclear reactors have had a sketchy history of disaster. In 1979, the United States saw its largest nuclear accident. One of the reactors in the 3 Mile Island nuclear generation station had a partial meltdown. The pumps that fed water into the reactor stopped pumping water, which caused the emergency shutdown within about 8 seconds. The control rods were fully dipped in to stop the reaction. However, the remaining heat was slow to dissipate, and since there was no water to remove heat from the reactor melted down. Now, studies done about the fallout showed no statistically significant increase in cancer rates. Cleanup of the area began in August 1979 and ended in 1993, and it cost us about $1 billion. In 1986, the Chernobyl nuclear power plant in Ukraine experienced a meltdown. Ironically, the engineers there were testing a safety system to see what would happen in the case of a power outage to the water circulation pipes. Nonetheless, the test was a spectacular failure, and the reactor experienced a steam explosion and subsequent fire that released radiation into the air for about 9 days, and the fallout zone was pretty much most of Europe. This caused nearby rivers and groundwater to be contaminated with radiation. About 4 square miles of a nearby forest saw all the trees die. In the aftermath, 237 people had radiation sickness, of which 31 died. The current consensus from the UN is that the total death count as a result of this accident was about 4,000. In 2011, a tsunami knocked out the power supply to the cooling systems in the Fukushima nuclear power plant in Japan. This caused a series of explosions and meltdowns in 4 of their nuclear reactors. The resulting spread of radiation spread throughout pretty much half the planet through the air. The debate about the fallout of this disaster are still occurring, and the scientific consensus takes a long time to figure out. So to prevent any potential misinformation, I'll end my discussion of that disaster here. Now, there's a new type of nuclear reactor being developed that uses nuclear fusion rather than fission. Nuclear fission is the combining of atomic nuclei rather than splitting them. Well, this is the reaction that occurs in stars. The reaction releases much more energy, and the potential for this type of power is massive, as it doesn't produce any nuclear waste. But it is still in very early development, and we just barely broke even in the amount of power we can get out of this reaction. Who knew harnessing the power of stars might be difficult? And now it's time for a history lesson in a closer look. Where I am standing right now is the gravesite of the beginning of the atomic age. a team of scientists led by Enrico Fermi and Walter Zinn created the first ever self-sustaining nuclear chain reaction in a lab underneath a football field at the University of Chicago.
August 2nd, 1939. Then President Franklin D. Roosevelt received a letter from Albert Einstein. In it, he described the research of Dr. Fermi, in which he was looking at using uranium as a new source of energy. However exciting this information could be, it soon turned dark. Einstein noted that this technology could also lead to the production of a devastatingly powerful weapon. It was World War II, and Einstein noted that Germany was aware of this work and began stockpiling uranium. Enrico Fermi was invited to Chicago and began work on the metallurgical laboratory as part of the Manhattan Project. The project was led by the United States with support from Canada and the United Kingdom. The race was on for the production of the first nuclear weapon. On December 2nd, 1942, the scientists succeeded in their goal, a controlled, sustained nuclear fission reaction.
Determining a university was not the best place to build a top-secret nuclear reactor, the United States Army established a site here, in what is now Red Gate Woods in Lamont, Illinois. In February 1943, the reactor was disassembled and rebuilt here, exactly where I am standing. The reactor here was always experimental, and the results were used to provide information to other reactors.
The reactor looked nothing like the ones today. It was essentially a pile of 10 tons of uranium metal and 41 tons of uranium oxide, all encased in 472 tons of these graphite blocks. But the goal was never electricity. These reactors barely produced 50 watts of power. You can't even power a light bulb with that. These reactors were used to produce plutonium for a bomb.
5, 4, 3, 2, 1.
This led to the development of the Trinity bomb, which successfully detonated in the New Mexico Alamogordo bomb range on July 16, 1945. Upon seeing the devastation of the weapon, the scientist who oversaw the project, Julius Robert Oppenheimer, remembered a verse from a Hindu holy book.
I remembered the line from the Hindu scripture, the Bhagavad Gita. Vishnu is trying to persuade the prince that he should do his duty, and to impress him takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds."
Afterwards, Oppenheimer and many scientists of his generation worked to prevent the spread of nuclear weapons, though he never regretted his part in the production of this weapon. Just a month after the test of the Trinity bomb, the United States dropped 2 nuclear bombs on Japan.
We cannot go back. There's a difference between knowledge and wisdom. Science gives us many things. The science that can power the world can be the science that ends the world. The same science that can cure diseases can create bioweapons. Here, on the other side of the woods, we're at Plot M. Underneath me is the nuclear waste from the Chicago pile reactors. One could hope that this stone, marking the disposal site, warning people not to dig here, could also serve as a warning to use knowledge wisely.